All right. Good afternoon. So today we are going to continue our transformation equation, and then we start more with so as I said on Monday class, these topics have many details. So make sure that you are following the lectures, and if you have any question or it was confusing, just ask me in the class or out of class. So any question before we start? All right. We were given with the plane stress element like this, 1 square, some stress and normal stress and shear stresses are applied. We would like to know if you rotate this state of stress element or if you cut it at the angle of phi, what would be the new terms for sigma and the shear stress and the new stress element. So we move from this to something like this. We would like to know what would be the sigma and the shear stress applied to this surface. So we derive this to equation which can produce or generate or calculate sigma and the shear as a function of phi. So the question was at which angle we are going to have the extreme value for the sigma on the normal stresses. Then I will know how should I cut or which plane is going to have the extreme value for the sigma and which angle or which plane is going to have the extreme value for tau. So we derived the extreme value for normal stress and the shear stress that I have. I'll bring them here. I will start with principal normal stresses. What would be the phi? The tangent of two phi p or principal normal stresses is going to be 2 tau xy divided by sigma x minus sigma y. This is how you can calculate the angle. And what would be the value for the sigma? It's going to be sigma prime 1 and 2. We are going to get two values because here we will get two answers. From the tangent inverse, we are going to get two answers. So we are going to get two values for sigma. I labeled as sigma prime 1 and 2. And shear stress at principal normal stress direction, it's always 0. So we don't have any shear stress if this one is at principal direction plane. We could find the extreme value for shear. What I did, just differentiate tau with respect to phi, set that equation equals to 0, and find the corresponding phi. I will label that with phi s, or principal shear stress direction. It's going to be negative sigma x minus sigma y divided by 2 tau xy. So you can find the corresponding angle. If I cut, or if you rotate, they have the same meaning. If you cut this plane, or if you rotate it at this angle, Phi. The value for sigma is gonna be, for both, is gonna be sigma x plus sigma y dividing by 2. And extreme value for the shear stress is gonna be positive and negative sigma x minus sigma y divided by 2 squared plus tau xy squared. So this is what we got on Monday class. Any question on this? We are going to work on class activities shortly, Pastor. I just want to make sure that you understand the process and each terms before we go forward. Yes?
For the sigma values, when you have inside the square root, like sigma x minus sigma y over 2, is all of that raised
Yes.
to 2?
Inside the parentheses.
Okay, thank you.
Yeah. Same thing here.
Okay.
All right. Couple of things. First, suppose I consider angle of 45. Theta equals to 45. The tangent of 45 is 1. If I add theta by 90, I will get 135. So the tangent of 135 is negative 1. If you change the angle, theta equals to 30 degree. The tangent of 30 degree is 1 over square root of 3. If you add theta by 90 degree, the tangent of 120 is going to be negative square root of 3. So the point is, by shifting the angle by 90 degree, the tangent multiplication is going to be always negative 1. One times negative 1 is negative 1. For this also, we have the same thing. The tangent of 30 times the tangent of 90 plus 30 square root of 1 over square root of 3 times negative square root of 3 is going to be negative 1. We can't prove that mathematically, but I just want to show you with some numbers. So now, if you look at these two, the principal normal direction and principal shear stress direction. If you multiply these two, tangent 2 phi p times tangent 2 phi s, you will get exactly negative 1. 2 tau xy over sigma x minus sigma y. Here we have just negative. If you flip this and put the negative behind that, you will get the other one. So the multiplication is going to be negative 1. So it tells me the difference between these two angles is 90 degrees. I put the absolute value because I don't know which one is greater than the other one. But the absolute value of the difference is going to be 90 degrees. If I cancel out these two, I can say always the principal direction and principal shear stress direction, they are 45 degree offset from each other. By just looking at this. All right, let's work on this. I just want to ask you to plug in the numbers and get some sense about stress transformation equation. Then I will finish this example. So we are given with
No, it's like I think it's delta. It's like that last line. You've got the tau 2. So that middle symbol you've got it equals -1 equals, what is that? Is that a sigma or oh, it's an arrow. Oh, gotcha. There we go.
Not letters at all. Thank you.
So if we have a stress element, plain stress element like this, with sigma x equals to 80, tau xy equals to 30, sigma y equals to 40, and since we don't have any stress on plane z, all times in this plane it's gonna be 0. So if I look from front side, I will see a square 1 sigma x applied to this plane that I don't show here because I just want to look at the square sigma x. I will see this tau xy, this one, and this sigma y pointing up. 40, 80, and 30. So I'm asking you to find the principal direction for this state of stress. Is that clear? So I would like to know what would be the principal direction. For this state of stress, it's a plane stress. How do I know that? Because there are no stresses applied on the shear on the plane Z.
Comes out to be like technically, that's like 60 or 80, 70%. You did 60 to 80, so 60 to 40. So there we go.
At number 46, logic. Did you start working on that? Which equation did you use? Okay, this one. So the value would be we are looking for phi p, which is 2 times whatever is the shear stress term is 30. And here sigma x is 80, sigma y is 40. So 60 divided by 40, or 3 divided by 2. Would you find the tangent inverse of this angle for me? Tangent inverse of 3 over 2 is going to be
56.31.
Thank you. 56.31. Okay, let's stick with 56. 56 degree is gonna be 2 VP. The other angle is 180 plus 56. We have two answers. Two angles, they're gonna have the same tangent. Is that clear? Alright. So 1 PP is gonna be 56 divided by 2, it's 28. The other one is 90 plus 28, which is 180. We have two angles. These are principal direction of this state of stress. Any question on the, yes?
For the angle VP, for the second angle, do you add 90 or is it 180?
I just divided by 2. 90 plus 28 is going to be 180. Alright, now the next question that I didn't ask you, but I would like to work on that, find the principal normal stresses, sigma 1 and sigma 2. It's going to be sigma prime 1. You should please see why do I use prime, not just sigma. Sigma x plus sigma y, AD plus 40 divided by 2 plus and minus square root of sigma x, AD, sigma y, 40 divided by 2 square plus tau square, which is 30 square. AD plus 40, 120 divided by 2, 60. 60 plus and minus square root of 80 minus 40, 40 divided by 2, 20, 20 square, 400, plus 900 is going to be 60 plus and minus square root of 1300. Sigma prime 1 is going to be 60 plus square root of 1300. It's going to be 96 almost megapascal. Sigma prime 2 is 60 minus square root of 1300. It's going to be 24 megapascal. So and if I ask you what would be the shear stress, you don't need to calculate. It's always 0 at the principal direction. Now, this is what it means. So if we have this plane stress element, sigma x is 80, sigma y is 40, and tau x is 30. At this state of stress, these are the value of the stresses. But if I cut it at the angle of 28, or if I rotate it by angle of 28, just clockwise, we are if this angle is 28, if I rotate it by the angle of 28 degree in counterclockwise direction, the stress applied in this plane is gonna be 96. The shear stress is gonna be 0. The stress applied in the other plane is gonna be 24. And the other arrows goes in this direction, 24, 96. Sigma prime 1, sigma prime 2. And no shear stress. We didn't change the loading, we just changed the plane. How did I change the plane? I just picked another plane which has the angle of 28 degrees from the original state of stress element. Just think in, this is the original state of stress element rotated by 28 degrees. The value of the stress, normal and shear stress are gonna change. We will get the principal direction normal stresses because the angle that we calculated was principal direction. Is that clear? We didn't change the loading, we just picked a different plane. And in this different plane, the value of the stress would be 96 and 24 and no shear stress. Any question? All right. I could ask you, you can pick this angle if you want. Just rotate it by 180, which is 90 degrees perpendicular to this. This arrow is gonna come here, and this 25 4 is gonna come here. So you will get something like this. If you rotate this by 180. Because 180 is 90 degree offset from 28, it means you can just rotate this by 90 degrees. So 96 comes here, 24 is coming here. Alright, I can ask you what would be the angle for principal shear stress. The tangent of 2PS is going to be negative of 2/10. Will someone calculate this angle for me? If I'm looking for the tangent inverse of 2/10.
33.69.
30?
33.69.
Thank you. Let me consider that a negative unit. Negative 34. Negative 34, the half of this angle is gonna be negative 17 degrees. The other angle is negative 180 minus 34, which is 146. .73 degrees positive. Now look at this. You could use this equation and find Phi S1 or use this one. The angle that I found is 28. So the absolute value of 28 minus Phi S equals to 45. So Phi S should be negative 17 to make it 45 degrees. So it's gonna come 45. Or 73, yeah, 28 minus 73 is going to be negative 45, which is absolute value is going to be 45. So either use this equation or this one, you can get the answers. So what would be the normal stresses at this plane? Sigma 1 and 2, sigma s at 1 and 2 is going to be sigma x plus sigma y divided by 2. AD plus 4D divided by 2 is going to be 60. And what would be the shear stress is going to be positive and negative of this square root, which is a square root of 1300, which is almost 36. So now I can draw the stress element at for the shear, extreme value for the shear. It's gonna be, I should rotate it by the negative 50, negative 17. Negative 17 means rotate it in clockwise direction by the angle of 17. So uh, 70. From the original coordinates, I rotated by the angle of 17. At this plane, sigma x or sigma x is 60. The other one also is 60. Tau xy is 36. It's gonna look like this. So by picking the different plane, I will get the different value for the shear stress and the normal stress. Any questions so far? All right. Before we move to Mohr circle, let me talk about a maximum shear stress and the difference between extreme value and the maximum shear stress. If you look at the principal normal stresses, sigma prime 1 and sigma prime 2, just look at this. Sigma x plus sigma y divided by 2 plus this and minus this. And compare with the extreme value of the shear stress. If you do that, you can say sigma prime 1 minus sigma prime 2 minus, this is sigma prime 1, sigma prime 2 is negative sigma x plus sigma y divided by 2. This negative times this negative is going to be positive. So I can cancel out these two terms. So sigma prime 1 minus sigma prime 2 is going to be 2 times this. So if I divide this by 2, I will get sigma prime 1 minus sigma prime 2 divided by 2 is going to be sigma x minus sigma y divided by 2 squared plus tau xy squared. So the difference between the principal normal stresses, it's going to give me the extreme value for the shear stress. But if you remember, for principal stresses, we have a third principal stress term which is going to be equal to 0, and we didn't talk about that because we just calculated sigma 1 and sigma 2, but the third one is always 0. So sigma prime 1 equals to 96, sigma prime 2 equals to 24, and sigma prime 3 equals to 0. Since I have three terms of the principal stresses, I can define 3 set of extreme value for the shear stress. This is one set. The other set is sigma prime 1 minus sigma prime 3 divided by 2, and sigma prime 2 minus sigma prime 3 minus, doesn't matter, divided by 2. I have 3 principal normal stresses, so I can define 3 set of extreme value for the shear stress. So how do I know that which one is the greatest one? Then I can call that maximum value for the shear stress. If you calculate these 3, you calculate the first two, sigma prime 1, sigma prime 2, and sigma prime 3. Then pick 3 things, sigma 1, sigma 2, and sigma 1, sigma 2, and sigma 3. And make sure that they are in order. Sigma 1 is greater than sigma 2, and both are greater than sigma 3. Now, look at these 3. Assign the greatest one to the sigma 1. If sigma prime 1 is greatest, just say sigma 1 equals to sigma prime 1. If this one is the greatest, just assign sigma prime 2 to sigma 1. Or if it happens for sigma prime 3, set that value equals to sigma 1. Then pick the middle one and the smallest value. After you do that, if I ask you which of them it's going to have the greatest value, since you ordered them, the difference between sigma 1 and the sigma 3 would be the greatest. So you can say the maximum value of the shear stress is going to be sigma 1 minus sigma 3 divided by 2. So again, for maximum shear stresses, you cannot say always this is the greatest value, because suppose sigma prime 1 is 96, sigma prime 2 is 24, and sigma prime 3 is 0. By using that equation, the tau extreme is going to be positive 36. But if you order them, which one is going to get the maximum value of sigma prime 1? So sigma 1 is going to be 96. Sigma 2 is going to be the middle one, is going to be 24, and the last one is going to be 0. So the difference between 96 and 0 is going to be the greatest value. 96 minus 0 divided by 2, positive 48. So if you use that equation, you could get the wrong answer. So the maximum shear stress would be 48. So to answer this question, what would be the maximum shear stress? What you need to do, you need to order the principal normal stresses in this form. Sigma 1 is greater than sigma 2 is greater than sigma 3. Then find this subtract, sigma 1 minus sigma 3 divided by 2 and introduce as a maximum shear stress. And I think that's all for stress transformation equations. Now we can move to the Mohr circuit. Any question before we move on? All right. The Mohr circle is a graphical approach or graphical method to visualize this equation that I explained here. You are given with a plane stress element like this. You would like to find principal direction, principal normal stresses, principal shear stress direction, and the value of normal stress at this direction and the shear stress at this direction. This is one way. The Mohr circle is a graphical approach to do this for us. So it's just another way to explain this equation. So let's do one class activity before we move forward. If this is x-axis and y-axis, I have point A with the coordinates of A and B, and point B with the coordinates of C and D. Just a simple thing. Calculate two things. The coordinates of the middle points, C or center, and the length of AB. MECH number 7. It's a random number, but okay. What do you think? Center. Let's start with the center.
Take the difference. For the x component, take the difference between C and A
So A minus C you mean,
over 2.
over 2, and I guess
The same thing.
B minus D. And for the length,
Pythagorean theorem. So A minus C squared plus B minus D squared all to the 1 half.
square. Okay. Number 41.
What's the
The question, do you agree with this or you want to change it then?
I agree.
Number 37. Zach.
What's the question?
Do you want to change it or you agree with this?
I agree with that.
So any different how? This is correct, but not this one.
Oh.
Is it C minus
No,
Would it plus C plus D?
it should be plus. It's at the middle, so we get the average of coordinates. So A plus C, because C is at the middle, divided by 2. B plus D divided by 2, it's gonna give us the coordinates.
That wasn't true.
Alright,
Sounded good.
any questions so far? Because we are gonna use this on Mohr circle. So what we are gonna do in the Mohr circle, we pick one point, which is representing point A. In this plane, you know that it's representing a cube. When I pick point A, I mean one point in this plane, somewhere here. Anyway, it's gonna happen in this plane, point A, and one point here in this plane, point B. So if you look from front side, you will see point A and point B. It can be anywhere in this plane. The Mohr circle has axis x and axis y. Axis x is representing the normal, axis y is representing the shear stress. Normal and the shear. Now, I'm looking at point A. Point A has two coordinates. It has the value for the normal stresses and it might have a value for the shear stresses. I just write sigma x and tau xy for point A. Point B, the same thing. What would be the coordinates of point B? Sigma y and tau xy acting to that. So we have more convention. Tensile stress is considered positive. Compressive stress considered negative for the normal. For the normal stresses, if the stress is tensile, then it's going to be positive. If this one is tensile, it's going to be positive. As you see, both are tensile. They are acting outward the plane, outward of this plane and this plane. So these two should get a positive value. For the shear stress, if the shear stress is trying to rotate this plane in clockwise, then we get the positive value for this. And if it's trying to rotate the cube or plane in counterclockwise direction, we get the negative value for this. Now look at this tau xy acting to point B. It's trying to rotate in clockwise. So this one is getting positive tau xy. But this one is trying to rotate the cube or the plane in the counterclockwise, so it's going to be negative value. So this is how you can find the coordinates of point A and B, and this is the only way that we use negative for the counterclockwise. We always use the counterclockwise positive except for the Mohr circle. In Mohr circle we have the exception. So as you will see in the rest of the semester, always the torque is making counterclockwise. We consider this as a positive, but for the Mohr circle it's going to be. Now, just locate point A and B on these two axes. So I assume that sigma x is greater than sigma y. Just so if this is sigma x and this is sigma y, and if tau xy is here, negative tau xy is right here. So point A has sigma x and negative tau xy. Point B has sigma y and positive tau xy. Connect these two. Connect these 2 points. If I ask you to find the center or middle points of this, center is going to be this plus this divided by 2, sigma x plus sigma y divided by 2 for the x component, and for the y component, since they have the same value but in opposite direction, this plus this is going to be 0. Just finding the coordinates of the middle point. The average of x and average of y. Shear stress is going to be 0. In this line, which point is going to be? The center is going to be, or the middle point is going to be right here. Now, draw a circle with this center and this radius, or this diameter. Something like this. With this center and this radius, I draw one circle. What is the radius of the circle? You answer this question. What would be the length of AB? It's going to be this. If I divide this by 2, I will get the radius. If I divide this by 2, if I want to move these 2 inside the square, I should use 4. So radius would be sigma x minus sigma y square plus negative tau xy square divided by 2. So this is radius and this is the center. I will continue tomorrow